right, so this is the last week before the exam. Our exam is on next Monday, and it only covers chapters 1 through 15. Today we're going to finish, we might finish through 14, hopefully, and we'll finish 15 in the exam review on Thursday. So now there's 3 homeworks due. This one's due Sunday. So I wanted, the reason being that we have no homework due here after the exam on Tuesday. So after today's lecture, you'll be able to do most of this homework, all the way through homework 8. So let's get started. And, one other thing I should tell you is if you go to the exam schedule here, you see that it only covers 1 through 15, but these practice exams and study guides go all the way through 18. So just ignore 16, 17, and 18. I haven't had a chance to cut those problems out yet, but your exam only goes through chapters 15. And right now, you don't know which room, unless you sign up for the conflict, and anybody who wants to can sign up for the conflict. Just go to Lon Kappa. You don't have to show me any documentation. Anybody who wants to can do that. But you don't have your room assignment yet. We're going to be divided into 3 rooms, and I'll give you your room assignment. I'll post it here later this week. So any questions on the upcoming exam or what you need to do for that? Okay, so let's just go to the document camera then right now. And last time what we did was we talked about, we just did an introduction to significance tests, and we looked at this one sample z-test. So what's the idea again? The idea is you see some effect, and you want to test whether that effect that you see is just due to chance variation, the luck of the draw, or if it's due to, there's some reason for it, some particular reason for it, not just chance variation. So you set up under the null a probability model, a simple box model, assuming that it is just due to chance, and then you see how likely you would be to get such a big effect between what you observe and what you would expect under the null just by the luck of the draw. So here's another example, which is a very typical example, that somebody makes a claim about a population, and you want to test that claim. You don't trust it. You think that maybe, for example, suppose a large university claims that their average ACT score of the incoming freshman class is 30. Okay, so that's the claim about this population. But we think they may be inflating their average. So to test their claim, what do? If we could get the ACT scores of the entire population, well, we could see whether that claim's true or not. And we wouldn't have to do a significance test. But generally speaking, you can't do that. In this case, it would be too expensive. We don't have all that information. So let's say we take a simple random sample of 50 students. So that's our sample size. And find that their average, our sample average, that's like X bar, our sample average, is 29.1. And this right here is our population average. This is the claim, and we want to look at this difference between what we observe, this is what we observe and what we expect. This difference of negative 0.9 is just due to chance variation or not. So we formulate the null and alternative hypothesis in terms of a box model, a probability model. So here's the null box, always represents the entire population. And in this case, the entire population is all the incoming freshmen. So there's thousands of tickets in this null box, and on each is written some ACT score. And the claim is that the box average is 30, and we think it's really less than that. We did get less, but is that a big enough difference that we can say this really probably isn't 30 or not? So now, we were given the standard deviation of the sample. We don't know sigma of the box. We were not given it, and often you're not. Usually you're not. But we can use this to estimate. We're going to use this, the sample, to make an estimate. And if our sample size is large enough, 50 students, we said that this estimate is pretty good. If it was less than 25, we're saying less than or equal to 25, we said we were going to adjust this and make an adjustment by making this a little bit bigger. Okay, but for now, let's just stick with say that's good enough. We have 50 students. So what's our null? Our null is that the professor's telling the truth. Or not the professor, the university claims. Why would they be lying? Well, sometimes they lie or not lie, they exaggerate or overestimate for the U.S. News and World Report ratings, and because they want to make their university look more selective than it might be to attract people. So we think they might be doing that, inflating it. Okay? So there's thousands of tickets. Why? For each thousands of tickets. Do I need to know the exact number of tickets inside the box? No, I don't. This is large N. This is large N, and that never enters into our formula unless we wanted to use that correction factor. This is such a small, little n is such a small fraction that we can ignore it, but I just want you to picture what we're doing. So there's thousands of tickets. On each is written what? An ACT score. Okay. You got it? And what's our alternative hypothesis? Our alternative hypothesis is that we think that it's really the average in here is less than 30. We think they're inflating it. It's a directional. We think it's less. Not just that it's different, but we think that it's less. So that's what our alternative is. So what do? We randomly draw out of here. We randomly draw. We draw randomly. N equals 50 tickets without, right? Without replacement. Because we don't want to get the same student twice. Without replacement. Okay? And what do we get? We take, of those 50 tickets, we get an average, and our average is, sure enough, less. But we get an observed average, our observed X bar, we can call it, equal to 29.1, with an observed with SD equal to 4.5. Okay? And what would we expect? We'd expect, wouldn't you expect, our expected average, sample average, is going to be mu, is going to be equal to 30. The same as mu. Okay, so this is just mu. So now we're going to do, what are we going to do? We want to know if this difference between observed minus expected, negative 0.9, if that is, is that likely to be due to chance or not? Well, we have to get a test statistic. So what's our test statistic going to be? I said compute the z test statistic, but why? If I asked you, would it be z or t? Okay, how do you know? Well, we have an unknown sigma, so that means, so it could be either. We have an unknown sigma, and we have a large sample size for the purposes of our course, and n is greater than 25. So we can use either. We can use either. And it's simpler to use z. You wouldn't be wrong if you used t. but it's simpler for us to use. It's simpler. So we're just going to use Z. Okay? It's easier. There's just one normal curve. Okay, so let's do it. So our Z is what? Always this difference, our observed minus our expected, over some standard error. And our standard error is for what? What are we talking about here? Averages, X bar. So this is for the average, or for X bar. These are all averages. So we have 29.1 minus 30 over, whoops, what is this? What is that? Well, do you remember? This is something you need to know. You need to remember this for the exam, so be sure. So how are you going to remember it? So let's just think. What is SE average? Pretend this is the exam. What are you going to do? SE is like an SD. So just write SD, right? It's like an SD. But it also depends on the sample size. And since it's an average, you're going to divide by the square root of n. So it involves the SD and the square root of n. So that is it, SD over the square root of n. And we're estimating this SD is really sigma, it's SD of the box, and we're estimating that with the 4.5, okay? So it's SD of the box, which is sigma. I'll just write SD of box of the population. And that is, we're going to estimate it with the 4.5, and then over the square root of, it's not these thousands of tickets here, it's n, which is 50. And I got 0.636. So that's what goes here. Okay? And then I got negative 1.4. So that's the z-score. And then now we use the normal curve to say, okay, we know the sampling distribution of the mean follows the normal curve. So we can draw a picture here. This is sort of the intuitive idea here. And this right here is as a z-score, zeros in the middle. But as a average, an ACT average, so this is as an ACT average, this is X bar right here, that is what? We'd expect mu, we'd expect 30. Now we got 29.1, and what that z-score tells us is how weird it is. Like it's only 0.9. You think, oh, probably wouldn't be that unusual. Well, where is it on here? Well, this tells you it's negative 1.4 in standard units. So we're going to look up to see, we want to get how unusual, how far out that is. So let's look up the middle area for that. So we're going to get, and that's what you'll have on your exam. You'll have a table. And let's look at that. And 1.4 is right here. So let's just round that to 84. 83.85. Okay, we can just round that to 84. And so that's 84% in the middle. Now, so how far out is that? Well, what's going to be on the two tails? 16 is going to be on the two tails together, right? So let's try to make it look pretty accurate, like 8% on each. So like 1.4 would be about maybe here and here. So that's negative 1.4 and positive 1.4. It's probably further out. That made it too big. That's supposed to only be 8%. Sorry. This right here is 8%, and that's our p-value. I made it, didn't really draw it too well to scale. But this from here out is 8%. So that's what's known as our p-value. And this is also 8% on that side. Has to add up to 100. So we can write our p is equal to 8%. So what do we conclude? Well, that depends on where you set the significance level And usually people set it at 5%. That's really standard. So let's just say it was 5% for a one-tailed test. All right, so if it's 5% for a one-tailed test, then this area right here would be 5%, not 8%. So let's just draw a null cutoff here. Let's just estimate it. So this right here, we can call our null cutoff. That's our significance for alpha equals 0.05. So this is our null cutoff, and it's typically 5%. And what does that mean? It means from here to here is 5%. So what's the conclusion? The conclusion is if we were at the 5% significance level, like that's the 5% right there. All right, so if our sample average was, if our difference was big enough, this is what, 29.1. 29.1 matched up with negative 1.4. Now, we would have had to get a bigger difference. It would have had to have been beyond here to say, it's suspicious. It doesn't look like that's unlikely to happen. It only happens 5% of the time. We would say we reject the null. We reject the null. That difference looks too big to be due to chance of it landing. Now it didn't. It landed in here. And this is just where this is our decision maker. Okay? And it landed in the middle here. Certainly, yeah, it's towards there, but it's 8%. So we're going to say we cannot reject the null, that it could be due to chance. Do you understand the idea? Okay. So that's what we're going to say. So we'll just say using that, so P is equal to 8%, which is greater than the 5% cutoff. So we can't reject the null. We're going with the null, that it could be due to chance. What does that mean? It means that the difference could be due to chance. The difference is kind of small, is what we said. So the difference is consistent with the null. It's small and could just be due to chance is the idea. Now, why do we say it this way? Why don't we say we accept the null? And some people do. Why don't we just say we accept the null? Because people don't want to get it confused with saying that we proved the null. They don't want to get it confused with that. We assume the null, so we really can't prove it. It's like the best example, an analogy, and if you're familiar with the American justice system, is that we assume innocence, and we assume as innocence. See, it's not like when we let somebody off, we haven't proved they're innocent. We just don't have enough to convict. We might have almost enough to convict, but not quite enough. So we say we don't have enough data to, it's not like we proved, okay, we don't have enough evidence to say that they're lying here. Okay, does that make sense? Questions on this? Now, if it was like way out here, we'd say, we have overwhelming evidence that he's lying, or that the university's lying, or not lying, but inflating their data. Okay, should we move on? Is everybody good? All right. Now, I'm wondering, why don't we skip this for now? You have a homework problem like it, so I'd like to do it, but I want to cover everything. And skip for now, and we'll see if we have time to go back to it. So, because I want to go on now to the t-test, because I said we could have used either there, right? But now if we have a small sample size with the unknown SD, like that, and we think that the population is normal inside the box, we're going to use the t. So let's do an example. We talked about this before with confidence intervals. It's the same exact idea now with significance tests. As you probably can see, there's a real strong connection between confidence intervals and significance tests or hypothesis tests. All right, so remember, if the SD's unknown, right? If you know it, don't use t. The sample size is small, and we said less than or equal to 25 is just for the purposes of this course. All right, if it's greater than 25, we're going to use z because it's simpler. And the central limit theorem allows us to do that. And the histogram for it's close to normal, okay? Close to normal. So let's say we're in a situation where these three things are true. Small, normal, unknown, SD, then we're going to use t. So we have to make these two adjustments. First, what are we going to do? We're going to make the sample. If we have to use our sample SD, we're going to make it a little bit bigger. Instead of dividing by n, we're going to divide by n minus 1. If you were doing it from scratch, this is how you do it. And this, just to help you with other courses, this is what's usually called S and given to you. This is the same thing as S. And it's given to you in most software printouts. You don't have to calculate it, okay? But let's say you just had SD. If you want to go back and forth between the two of them, they just differ. Look at this. The SD is divided by n, and the SD or S, SD plus, a little bit bigger, is divided by n minus 1. So if you want to go back and forth between the two of them, like if you had SD, like this, and you wanted to change it to this, you just multiply, you'd multiply by the square root of n. That would get rid of this. So imagine you multiply by the square root of n. That would cancel that out, and then divide by n minus 1. And the way you can remember it is SD plus is a little bit bigger, and n over n minus 1 is a little bigger than 1. So you're going to make it a little bit bigger. If you were going in the other direction, and you had SD plus, and you wanted to change it to SD, you would just flip it and multiply by something a little bit smaller. So this is what you need to remember, that SD, it's always greater, but the difference becomes negligible as n gets large. Okay, for example, I decided to make the cutoff 26. What happens when SD plus is going to be equal to what? Let's say you had SD and your sample size was 26. I would just multiply it by 26 over 25, which is equal to 1.02 times SD. So it really wouldn't make much of a difference. And if your sample size gets even larger, that becomes closer and closer to 1. So for the purposes, we're doing a lot of approximations so you can get the ideas. And so it doesn't make sense to be more exact than the tables we're using and so forth. So that's the idea. And so let's move on. Okay. So maybe I should just give you one other piece of information while we're on this front page, because you'll probably be looking back at it. So what about SE plus for the average? How would that compare? How do you do that? Well, that's just taking SD plus over the square root of n. And that's what you do in your other courses, because you're usually just given S, right? And you just divide by the square root of n. That's our square root law. But if you were just given SD of the sample, not SD plus, then that's the same thing as what? You don't have to change to SD plus first if you don't want to. You could just do this. It's the same thing. Just divide by n minus 1 there. So you can divide by n minus 1 down there or up here. Either one, it's the same. Okay, whichever is more convenient or whatever is easier for you to do. So let's move on. Now, we're going to go back and look at the example we did last time. The first example we did back on, just to show it to you, it was from last Thursday. It was right here, this example. We're going to do the same example that's taken from my own experience when I taught big courses in the math department. And I thought, was the main lecturer and I had lots of little sections under me. And I thought, I bet this early morning class, people who sign up for the 8 o'clock class, aren't just a random selection of people. And they will get a higher average. So we tested that, and I knew the population standard deviation, but let's say I didn't know the population standard deviation, and let's say the section really only had 16 students. Then we'd do the same problem, but we would use T. So let's do it. All right. So, so a large, just to refresh your memory, has 1,000 students. On the midterm exam, the class average was 70. All right, and the scores are approximately normally distributed. Let's make these assumptions, and the standard deviation is unknown. It's suggested that the early morning section has more serious students and would therefore have higher scores. This section has only 16 students. So there's our small unknown sample. SD is unknown and approximately normal. We can use T. All right, their average was 75, and their SD is 12. So the question is whether this 5-point difference between what we observe and what we expect, what we expect under the null, that it was just, there's nothing special about that class, they're just a random selection, that 5-point difference is real, meaning due to some real cause, or whether it's simply due to chance variation. All right, so we're going to formulate the null and the alternative, and it's the same, we'll just say same as before, that the null is always that the effect you see, this 5-point difference, is just due to chance, just due to the luck of the draw. So we make this box model based on that, just due to the luck of the draw, that in the class, the whole class has a class average of 70. There's 1,000 tickets, on each is written a score. And this time we don't know the standard deviation of the class. All right? And then, what's the alternative say? The alternative said this 5-point difference is too big to be due to chance. Too big. If we randomly sampled 16 people from here, it would be very unusual to get such a big difference as observed average of 75. So we randomly sample n equals 16, again without replacement, and get an observed x bar equal to 75. When we expect, our expected x bar, mu, is equal to 70. So this 5-point difference, 70 minus 75, 75 minus 70. All right, so now, though, we don't have an SD here, and we're going to use T. So we've got to say, okay, so we're going to do SD plus, okay? Our SD is 12, but we're going to make it a little bit bigger to account for the uncertainty. This it's a small sample, so we don't have it's likely to be an underestimate. So we're going to make it just a little bit bigger by a factor of what? What do you think it's going to be? You should write it in so you remember, like right away. What do you think it would be? We're going to make it bigger. So is it 16 over 15 or 15 over 16? You want to make it bigger, so you're going to do what? 16 over 15. That's all you have to think. Square root of what? 16, n over n minus 1 or n minus 1 over n. You want to make this bigger, so you just do 16 over 15. And that will make it a little bit bigger. Okay? So, now, you can calculate that, but now what are we going to do? Let's just remember what we're going to do. So, let's remember. So we're going to do, our statistic is still going to be observed minus expected over a standard error. And it's for the averages, okay? Standard error for the average, for X bar. But now we're just going to put a plus here. We just want to get that t-stat. So this numerator is not going to change. Our observed minus our expected. That's 75 is what we observed in our sample minus 70, that 5-point difference. So that is the same. Now, how are we going to change this? We could calculate this out and then divide by, let's just write it down here so you remember. So we have SE plus average. Now, easiest way probably to remember it is doing this over the square root of n. That's fine. But it's kind of easier. That's the same exact thing as doing SD over the square root of n minus 1. So you could do that too. And that's just easier. For me, it's 12 over the square root of 12. Instead of saying 12 over the square root of 16 like we usually would do, what do we put down there? 15. So that's the same answer. And so I got approximately 3.1. And that's what goes here, and that's what goes here. Now, if we were doing the z statistic, it would just be 12 over the square root of 16, so it would be 3 instead of 3.1. So the t-stat right here is just uses a little bit more error here. So I got 1.61. All right. Of course, you could have done that and just whatever result you got here, same thing, then divide by square root of 16. Any questions on that? So that's our t. Now, that's what we're doing right here. That's our t. And now we're going to draw our picture. Okay, so now, how are we going to do this? This is our t. And it's symmetrical, just like z. It's symmetrical. It's centered at 0. All right? And then underneath it, we're going to have what our x bar is, what our exam average is, and that's in the middle of 70, 70. And we want to know where to place 75 on here. How far out do we go? And this is how far out we go. That's what it tells us. 161. Okay? So let's say there's two ways we can look on the p-value calculator if you want. Why don't we do that first? And just so you can know how to do this on there. So let's go to our PC. And here's our p-value calculator right here. All right, so now the t distribution. So do you remember the degrees of freedom? We talked about them last time. Do you remember how to calculate that? That it's 1 less than your sample size. So our sample size is 16. 16, so it would be 15 degrees of freedom. Because the t-curves change. It has a different t-curve for each degree of freedom. So we have 15 degrees of freedom. And what did we calculate our t-value to be? 1.61. So let's put that in. All right. And now we just want the right-hand tail for now. Because we expect the alternative was that the kids were that class was going to do better. We expected them to do better. All right? So now we'll compute the p-value, and that's our p-value right there. So how do you read this? this says our t, we knew this, and this gives us our percent right here as a decimal. So our p-value is 6.412%. So can we reject the null? We'd have to get, what would we have to get to reject the null? We'd have to get further out. You can see we'd have to get a p-value, let's put 5% in here, and then we'd have to get a critical value here. We'd have to have gotten a bigger t-stat of 1.753. We didn't get that big, okay? We only got 1.61. So we can't reject the null. We're going to say that could easily be due to chance. It's not small enough. Our p-value is not small enough. So that's how we do it. If we were going to be doing it on the calculator, let's do it on our table, and then we can only make an approximation. So let's go back to the PC. Any questions on how to do this on the here? Okay. So let's go back to the all right, so now let's write that down first, that what we actually got. Okay, so we actually said that this 75 matches up with, that 75 matches up with 1.61, and that our p-value right here was approximately 6.4%. That's our p. Sorry, that's our p. So that 5-point difference, so we can't reject the null. Now let's say we were doing it with this is using the p-value calculator. So this was using calculator. But what if we had to do it using the table? Let's try it using the table. Okay, so what would we do? We'd look at this first of all, degrees of freedom. Where did we put that down? We have to say the degrees of freedom, compute p using the student's, okay, there's a different degree curve for each number of degrees of freedom, where the degrees of freedom are n minus 1. So our degrees of freedom is equal to 16 minus 1, which is 15. It refers to, these degrees of freedom refers to how many deviations go into calculating the error around your model. We're estimating these means, and we're saying how much error is there around our model. Well, we have how many calculations went into it. You'd think 16 went into it. But remember, the error around the model is our standard deviation around our standard error, and that really only had 15 degrees of freedom because, remember, the deviations always have to sum to 0. So if you knew 15 of them, those are free to vary, but the last one would be determined. So that's how you can think of why. And as you get more and more degrees of freedom, you get more and more information, and you get closer and closer to the normal curve. And then the t-curve will look very much like the normal curve. Now let's look at our, let's go to the back of the book, and let's say we were doing this. What information do we need? We need to figure out this 1.61. It's not so simple like with the z-curve, with the normal curve. So we have to keep this in mind, the 15 degrees of freedom. So this is what you'll see on your exam, this exact table, and let's look at it. All right. So first of all, 15 degrees of freedom, so ignore everything except this line, 15 degrees right here, okay? Ignore everything else, you're just looking at this line, and you're trying to find 1.61, that's our t. So you go across, and you see how 1.61 is in between these two values. So you look up here, and this tells you this is what we actually wanted this time, just the right-hand tail. Okay? So it tells us that our p-value, so we know our p-value is what? Is just between 5 and 10%. Somewhere in between 5% and we would have had to get bigger. Remember, we would have had to get bigger than 1.75 to get significance. All right, we found out that it was 6.4%, but from this table, all you know is it's between 5% and 10%. It's closer to 5%, it's closer to 1.75, so you could think it's closer, but you couldn't estimate it. All I'd ask you on a test is to say it's between 5 and 10%. Does everybody understand how to read that? Raise your hand if you don't. That's 5%. This tells you, these numbers tells you the area in this the shaded region. What are these above? These were the middle areas we were using for confidence intervals. These were for confidence intervals. That's what these were. But these are the area of the right-hand tail. Okay, does everybody understand now? Okay, so let's write that down and then we can move on. Okay, so using the table, let's say, find P using the table. So let's do that. So using the table, P is between 5% and 10%. Because what? Because 1.61 is between, oh gosh, now I forget the two values. Sorry. Is between those two values, which were, for 15 degrees of freedom, 1.34 and 1.75. Okay. So, 15 degrees of freedom, find P by using the t-table. We did. Should we reject the null? No. Because P is equal to 6.4%, which is greater than 5%. So we can't reject the null at the 5% cutoff. Any questions? Okay. You see why it's simpler to use Z. That's why I like it. Yes, question? What did you say?
In the t-table, the corresponding values in 50 and 80%.
For 80%? For
Never mind, it's okay.
I think, are you talking about confidence intervals? Yeah. When we do confidence intervals, we're going to use that middle area. So her question was, well, how do you find it for confidence intervals as opposed to p-values? Why do I have these little numbers up here? So just because the confidence interval it's just because of the way this table is written. So this only gives you right here the area of the tail. So for example, if we wanted to find an 80% confidence interval with the 15 degrees of freedom, what would we do here? We'd say 10% here, 10% here, and that would be 80% in the middle. So the corresponding confidence intervals would be between 80% and 90%. Does that help you? Between 5 and 10%. I think when we get to two-tailed t-test, you'll understand a little better. We're going to do that really soon. Okay, so here's our chart again that we went over last time. And now we're going to do a two-sample z-test. Are we already on that? Yep. Okay, let's do the two-sample. Z. So it usually, it's much more common to do a two-sample Z or T test rather than a one-sample. Because often you want to know if, like, you have two samples, like you want to compare two groups, like males versus females. I like on some, like, for example, do males or females do better in Stat 100? And we'll see some difference between their exam scores. Is that significant? There's always going to, some question like that. Or treatment and control, like the experiment we're doing right now. Do people learn better online or in person? So we're seeing some difference, but how big a difference, could it just be due to the luck of the draw? So you usually have, much more often than having a one sample, you'll have a two sample. So how do we do a two sample test? So, all right, so if our samples come from, if they're independent samples, like how well the males do doesn't affect how well the females do, if they're just independent of each other, or how well people do in the in-person class doesn't affect how well they do in the online, if they're independent of each other, then we can use this statistic that's just our observed difference minus the expected difference under the null, divided by the standard error of the difference. Now, if our null hypothesis is, which is often the case, is that the two population averages or percentages are the same, which it certainly is for the testing the in-person class, the test scores versus the online people. Why I would assume they'd be the same. I'm testing that. Or males and females, you'd assume that they'd be equal. Then the expected difference right here under the null, this is usually 0. Doesn't have to be, but in the examples we're going to be looking at, it is. So that just boils down to our observed difference over the standard error of the difference. Now, how do you compute the standard error of the difference? Let me just give you an example, an intuitive example. So suppose we have two populations, population A and you have population B. And the null, and you have like lots of people in both. And the null is you have some average here and some average here in the population. And let's say our null is that they're the same. Okay, so the null is that those two means are the same. It could be males and females or treatment and control, whatever. That these two are the same. Then, of course, we randomly sample n from each, or n's can be different. They don't have to be the same. We take a random sample, and we get a sample average here, and we get a for A, and we get another one for B. And let's say they're different. Just by the luck of the draw, they're bound to be somewhat different, right? Even if they're the same in here. And let's just make up an example. Let's say this is 100, and let's say that's 90. All right, so we have this observed difference of 10. But how likely is it? What's our standard error? How do we calculate that? Well, each one of these, we can calculate a standard error the usual way. So let's say we got a standard error for this sample average, and this is based on the standard deviation of the box and the sample size. And let's just say it was 4 after we did that calculation. Let's say we got a different one here. Okay? So they're both bouncing around. So what's the idea here? So the difference is what? Our observed difference is what? Well, from here, we have 100 plus or minus 4, right, from this sample. And then we're saying our difference minus from this one, we have 90 plus or minus 3, right? So that means, so what's our difference? Well, we know that our difference is 10. 100 minus 90 is 10. But here's the deal. Plus or minus what? You see this, think about it. You could get, let's say you got a 4 here and a 3 here. That would just be 4 minus 3, 1. But what if you got a 4 here and a negative 3 here? So that would be 4 minus negative 3. That would be 7. So how do we combine those differences? That's the idea. Well, think about it. if the key is, if they're independent, you can imagine the differences like the Pythagorean theorem here. You can say, okay, whatever you get here, straight up and down, this is our standard error for the first sample, doesn't give you any clue of this one. It's not pointing, this way or that way, right? It doesn't give you any clue. They're orthogonal or independent. So you can think of it like the Pythagorean theorem here, that when we're really, now we're subtracting them, but it's basically the part that we're interested in is how these errors are. And do you see how it's really not adding or subtract? It's plus or minus, minus, plus or, so you can think of them as adding. So it's like a squared plus b squared equals c squared. So this is the standard error of the difference. We have more variability than either one of them. We have two sources of error, so it's going to be bigger than either one of them, of course, but it's going to be smaller than their sum of 7, because the positives and negatives are going to cancel out. There's only one way to get 7. So the idea is this little picture here, and so the standard error of the difference, like the Pythagorean theorem, is the square root of the sum of their squares. And basically the idea is that the variances, I've said this before many times, that the variance of the sum, the variance, like if you square both sides, so now we have, instead of the standard error, we have a variance. So we have a variance, the variance of like a, it's like a plus b, a plus or minus b is equal to what? The variance, if you squared this side, you'd get s, the variance of a plus the variance of b. And so this is very important. It depends. The proof, again, I wrote it as simply as I could, and it's not hard to see. It's just algebra. So that's the idea. So how do we combine them? This part right here, this is 100 minus 90. That part's 10. And it's this part that we wanted to know, plus or minus what? What's going to be our error? And our error is going to be what goes in there, right there. Our standard error for the difference is going to be what? For the square root of 4 squared plus 3 squared, which is equal to 5. So that's how and you check. Make sure that it's bigger than either one of them, but smaller than the sum. That's how you do it. So, of course, it does not apply if the two samples are dependent. So now we can use that, just that Pythagorean theorem, to figure out the standard error for the difference, and it will just be the same thing we did before. So let's see how many more examples we do here. Okay. All right. So, all right, so this is just the two sample Z for comparing averages, and I like this one because they did exactly, just did a two sample Z test in this article. In the New England Journal of Medicine, back when this diet was very popular, called the Atkins diet. Diets just cycle around. It was called Stillman diet, and I don't know. They just keep recycling the same diets over and over and over again. I've seen a lifetime of them because I used to be care more about that kind of thing. So I think I even went on this one. So anyways, so I was very interested in it, and I read this article. So this is from the New England Journal of Medicine. They did a two sample Z test. All right. So the subjects were 63 obese men and women. 33 people were randomly assigned to the Atkins diet, and 30 were randomly assigned to the conventional diet. So the Atkins is one of these high protein diets. high calorie, high protein, and the other one was just your traditional low calorie diet. Okay, so after 3 months, the Atkins group lost an average of 6.8% of their body weight. So for like a 200-pound person, that would be what? 13.6 pounds. Well, the low-cal group lost an average of only like 2.7%. For a 200-pound person, that would be 5.4 pounds. Okay, so could the difference in weight loss be due to chance, or did the Atkins diet really work better than the low-cal? Set up a box model, state the null and alternative, find Z and P. Okay, so let's do that. So now we have, imagine that there's lots of people who want to lose weight, and we randomly selected, even though this wasn't quite the way it's done, but this is the method that's used based on this idea, that you have two independent populations here, okay? So you have all these people who want to lose weight, and from these people, the Atkins group, and here's the low-cal group. And they each have this null box, and this represents, so these two null boxes, they represent the entire population. So in these boxes, in both of these boxes, this one and this one, both have, I don't know, thousands, maybe millions. Let's just say thousands, it doesn't really matter. Thousands of tickets on each is written a number. It's written a weight loss. Now it's written as a percent, but let's think about it. Does that mean the numbers on here are 0 ones? Like, is this a percent problem? Like if we categorized it into the percent who lost weight and the percent who didn't? No, this percent is just a number. We're not going to treat it as, this is not a 0-1 box. Instead of just writing the number of pounds, they wrote percents, okay? Percent of weight loss. So this is an average problem. So we have an average weight loss here and an average weight loss here. So that's for the Atkins, and this is for the low-cal, okay? And we don't know what they are, but our null is that they are the same, okay? So this is our null, is that the average, if in our sample they're different, but that's just due to the luck of the draw. The null is that in the population, they're the same, these two. We didn't necessarily say their standard deviation is the same, though. So we have a sigma for each. We also don't know, and we also don't know. And we're going to estimate this from our sample. Okay, so now, what did we get? Here we got an X bar for the Atkins equal to 6.8, with a standard deviation for the Atkins equal to 5. These are rounded numbers. And this one was an X bar for the low-cal equal to 2.7, and a standard deviation here equal to 3.7. All right, so we're going to use these numbers. We're not going to do a t-test because why? The sample size was n equals 33 here. It was without replacement, but so many tickets it doesn't matter, and n equals 30 here, okay? So with our rounding and so forth, it doesn't make any difference if we use the Z or the T. I can't remember if what they did. I think they actually used the Z, but they might have used the T. All right, so now we're going to get the same result, pretty much, within 2 decimal places. All right, so now we did this, and now what are we going to do? Okay, so for here, for each one, we're going to figure out a standard error of the average for this one and a standard error of the average for that one. And we're just going to do that by SD over root n, which is 5 over the square root of 33 here. And here it was 3.7 over the square root of 30. Let's just leave it like that. All right? Now, what are we going to do? So that's what we got. Now, what are we going to do? We're going to do a z-test. So what's our z-test? We're looking at the difference between these two. What is the difference? 6.8 minus 2.7. So that's a difference of 4.1, okay? And we have to, so it's going to be our observed difference of 4.1 minus our expected difference under the null. And that's just 0, no difference. That's just 0 over our standard error for the difference. Okay, that's just 0. So we're just going to leave that off. And so it's just the difference between the two of them. 6.8 minus 2.7. And now it's just this. So I think the easiest way, I left it in this form, it's just easier for me to do this. Square root of, let's square this one. So if we, it's going to be the square root of this squared plus that squared. So if we square this one, we'll get 25. I'll just do 5 squared. 5 squared over 33 plus, if I square that one, I get 3.7 squared over 30. It's just just have less error. And so I got 4.1, and I checked over 1.1. And that was equal to 3.72. So that's the z-score. And if you look at this as a z, do you think don't you know that's going to be really far out on the curve? A z-score of 3.72, don't you know that's going to be significant right away? 3 sigma, that's almost 4 sigma. That's going to be hugely significant. And we can draw it, but this is a nice thing, you just should know right away. So if we drew it, it would be just hugely significant because what do we have here? This is as our z, and this is as our average weight loss difference. So what is this? This is our average difference. Weight loss difference. We'd expect it to be 0, but we got 4.1, and 4.1, we got 4.1 in the numerator here, 4.1, not pounds, but percent weight loss difference, and this matched up with 3.72. So between 3.72 and negative 3.72 is approximately 99.98%. So this tiny, tiny bit, this p-value right here, just that little dot, it goes on forever, but it's very, very small. And it's p equal to 100 minus 0.02 in the tail, so that's 0.01%. And that's less than 1%, which is a highly significant result. This is the null cutoff for high significance. For calling something highly significant. 5% is just for calling it significant. This is for calling it highly significant. So we are going to reject the null. That's like a tiny, tiny chance. And conclude what? So we're going to reject the null because it's less than 1%, that p-value. Reject null and conclude the result is highly significant, and conclude that there's highly significant means there's extremely strong evidence to reject the null, that it was just due to chance, and say there's a reason for it. And conclude that the Atkins, in terms of losing weight, works better. Atkins works better than low-cal for losing weight. But please, I don't recommend this diet. It's all meat all the time, so it's terrible for the planet. If you just want to lose weight, and then, in the short term, 3 months, I looked at 6 months, it was less. By a year or two, neither diet worked great. They're both about the same. People gain back the weight. But if you wanted to lose weight, it's amazingly, I tried it for a short period if you just want to eat for an occasion or something. But it's sickening. All meat all the time. Oh, gosh. You can eat as much fat and meat as you want protein. But it was so popular, I put bakeries out of business. It was so awful. From after that, I just eat bread all the time. I became almost a vegetarian after this diet. It was so awful. So I don't recommend it at all. And I gained all the way back, and terrible. Okay, so but if you just want to lose weight, that's the way to go. Now, just 1 and 2 tail t-tests. All right, let's talk about this, because we've been doing these one-tail tests. What does it mean to do a one-tail versus a two-tail t-test? All right, so if you specify a direction to the alternative, like if you think one diet actually works better than the other, and you know that ahead of time because you have some evidence in the lab or something, then you do a one-tail test. The tests we've been doing have all been one-tailed because we think we're pretty sure which direction it's going to go. Now, if you don't specify a direction to the alternative and just specify an inequality, that's called a two-tail test. Now, they both are going to yield the same z, right? The same z. It's just whether, when you're calculating a p-value, whether you calculate the area of two tails or just one tail. So which test should you use, okay? So that depends on how much knowledge you have ahead of time. What alternative makes sense for the situation? Okay, so here's the deal. Let's do it in the context of what we just did. All right, we thought, okay, we did a one tail. We said our alternative was that the Atkins worked better, right? So that's what we thought. So if we thought Atkins works better, why? Because we had some previous data on it, and we were pretty sure it was going to work better. Then what we do is we can do a one tail. I'm not putting the exact we found, but this is what we do. All right? So we found that. So P is equal to the area of one tail. Let's say we thought it was worse. Let's say we thought it worked worse. The Atkins is worse. Then we'd put it here if the other one worked better. We'd get the same we'd get the same area, the same z, but we'd just put it here. It would be the area of that. And the p-value would be the area of one tail. But what if we didn't know? Often, you really don't know. This is the case I was in exactly with the in-person and online. I'm doing a two-tail test because I have no idea which is going to work better. In fact, I thought the in-class would work better, but I wasn't sure. I thought there's reasons for both. So I would do a two-tail. So if I thought that the Atkins was just going to be different than the low-cal, but I didn't know which direction. That's what I thought. Probably different, but I didn't know which direction. This happens all the time too. Then you're going to get the same z, but now you'd have the same exact z, but now instead of just doing the one tail, you have to do the two tails. So it's just double, you get the area of both tails. So you get double the p-value. So p is equal to area of both tails, two tails. Okay? Now, what people do, now if you ever submit, almost all journals want you to do two-tailed tests. And most software is going to give you the two-tailed test. The reason for it is to avoid something called p-hacking, data snooping. Like what people do, they want a low p-value because they want to reject the null and say something works. But they really don't know ahead of time. So they look at the data, and afterwards they say, I knew before, so I'm just going to cut my p-value in half. And then you can get significance. So remember, you formulate your hypothesis before looking at the data. After you look at the data, you know which way the difference went. So it's cheating to use that knowledge to formulate your hypothesis. And it's called data snooping, p-hacking. It's really, it's terrible. It's cheating. So to guard against that, many people in software programs always, no matter what, use two-sided p-values. But when you're understanding it, to learn it, if you're really trying to discover something, and doing it, not trying to just get something published, it makes more sense to use the p-value that fits the correct alternative hypothesis. But you end up just always using the two-tailed. So the default is always two-tailed. Do you understand why? Because people want to get that lower p-value, and they want to guard against cheating. And you don't know if people looked at it after or before. Okay, so that's the idea. And now, let's see what we should do here. The two sample, do we have time? Let's see, what time do we have? Just so you can get started, what I could do is just skip to the two sample and we'll skip this for now. And just to get you started so you can do the two sample t-test, and then you'd have everything before the skip for now. We'll go back and I'll either post these or go through them again next time. But let's just do chapter 15 is just one page. All right. And how are we going to change it? Let's just look. This is what we did for the two sample Z. The only change we're going to put in is instead of SE, we're going to have SE plus for both of these. Square root of SE plus, okay? That's the only change. So let's do it. And we'll also answer some questions about two-sided and one-sided that comes up all the time. It's not special to the t-test. I just cover it here. All right. So now we are going to look at this. In the last chapter, we used the two sample z-test. All right. But if our sample sizes are small, drawn from a roughly normal population, small, normal, with unknown, let's just use the t. Okay. And the only difference is this. Instead of SE for difference, we have SE plus for difference. That's the only difference, except what do you do with the degrees of freedom? Okay? These two. So, all right. Well, this is problematic because remember I said that these t-curves are really the exact distribution. If you have a normal population and you don't know the standard deviation of the population, then your sample average actually exactly follows a t-curve with n-1 degrees of freedom. But the two sample t doesn't exactly follow any t-curve. Doesn't. So what do you do with these degrees of freedom? You do what, like people do this approximation. You'll see this complicated formulas, a Satterth weighted approximation, whatever. You'll see very complicated formulas. But they're not right. I mean, they're not exact, right? So for the purposes of this course, let's just keep it really simple and just very conservative, and we're just going to use n-1, where it's the smaller sample size. That's the most conservative approach. So that will give us the biggest error bars, and so if we get significance here, we know we get it whatever we do. So that's what we're going to do. So we're just going to take the smaller sample size and use that n-1. All right, now we're ready to roll here. So a randomized double-blind test was done to test the effectiveness of a drug to improve memory. This is hypothetical, made up. I made this up. 20 patients took the drug, small sample size, 16 took the placebo. Patients were given a pre and post memory score, 15 words to recall, and this is the improvement score. Post-test minus pre-test, okay? So this is their mean, how much they improved. Here's the drug, here's the placebo, and this was our data. So first, what is the null? Just think, what is the null? The null is always what? That the difference is 0 between the two of them, right? That there's no difference between the drug and the placebo. We just happen to see a difference in our sample. Now, suppose you have prior evidence that the drug worked, okay? You've tested it before, you've seen it work. Now, like you've done it with rats or whatever, and now with now it's time to really do a clinical trial. You know it's safe in the laboratory, blah, blah, blah. And you see that it works, then you can say it's greater than, okay? Because you have a reason to believe that. And you can say, you can use a one-sided. But suppose you have no idea if the drug works at the start of the study. But after looking at, you cheat, you data snoop, and then you say, hey, we came out ahead. Now, you get the same exact data, but can you use this? No. You have to use not equal to because you cheated. You have to do it beforehand. You have to make your hypothesis ahead of time. And so that's why it should be not equal to, and this is the two-sided. All right, let's compute the t-statistics and how many degrees of freedom, all that. Okay, first of all, degrees of freedom is going to be easy. We're just going to take our smaller sample size, which is 16. So it's n minus 1 for smaller n. So we get 15 again. Sorry, I'm using 15 again. There's nothing special about that number. I just did it. All right. Now, our t is, you should know this by heart, observed minus expected. It's a difference. Minus expected difference, and that's just 0 over. Now it's standard error plus for the difference. All right. So our numerator is 3 minus 1. That's easy. But now how are we going to do this one? Well, it's going to be the square root of something squared plus something squared. So what can I do? Now, I could do SD plus over n, or I could just do what? Do you see what I could do here? What I'm going to use is, all right, I'll do it both ways. So if I wanted, this is SD plus. If I wanted to change this 4, I would say 4 times what? The square root of sample size is 20. So is it going to be 20 over 19 or 19 over 20? 20 over 19. And this one would be 3. I'm going to make it a little bigger. It would be 16 over 15. You could do that and use that. Let me just remind you what we're doing here because this is kind of confusing. So let's just say it. So the standard error plus for the drug is what? It could be SD plus, so you could use that, but you got right there, over the square root of n, right, which is 20, square root of 20. But that's the same thing as using SD over the square root of 19. So either one, which would be equal to, I find it easier to do that, 4 over the square root of 19. Okay, that would be for the drug. And then for the placebo, what would it be? SE plus for the placebo would be what? 3 over the square root of what? N minus 1, 15. Can you even read that? That says 3 over the square root of 15. It's just easier for me to do that math because then when you square it, look what happens when you square it. So it's this one squared and that one squared. So when you square this one, right here, you'll get 4 squared, which is 16 over 19. And here you'll get 3 squared, which is 9 over 15 when you square those two. Does that make sense? Is that easier? That's just 4 squared. I'm just squaring those two and adding them together. So I got 2 over 1.2, which is equal to 1.67. Wow, am I running out of time? I can just finish up here. So now if we wanted to find the p-value for both of them, what would we do? Okay, so now we have this, we're going to say, okay, so we have t is 1.67. So t is equal to 1.67. And if I use the p-value calculator, I got 5.8 here. All right. Now, for the one-sided p, find the p-value. So for the two-sided p, it's going to be and this would be 5.8. It would equal 11.6%. This would be the two-sided. I use the p-value calculator here. And for the one-sided, it would be what? Half of that, 5.8%. If you use z, would your p-values be bigger or smaller? It's always smaller. P-values using z are always smaller. Why? Are always smaller. You know why? Because then t. Because t has fat tails, and the p-value is how much it's in the tails. It has more uncertainty. So bigger p-values. And I can show you, just so you know what you're doing, if you, with this 1.67, if you went to the, I'll just show you very quickly, if you went to the PC, and we go to the PC here, and here we are, and we had a t 15 degrees of freedom, and it's 1.67. So now for a right-hand tail, you could compute the p-value, and that's where I got the 5.8. For two tails, you could click here, and you see the area of the two tails. That's where I got the 11.56. I just rounded. So you can, you might as well use this to familiarize yourself. Okay? So we've covered everything you need to know for the exam, and we'll fill in those two examples. I'll either post them online or just we could work through them together, and we'll have a review next time. So you'll know exactly what you need to know for the exam on Monday.